My name is Mauro Filippini. I am at the Department of Mechanical Engineering at Polytechnic. I will present this paper on titanium aluminides. So titanium aluminides, it's an intermetallic alloy, so you might not be familiar with it. And but it's widely used nowadays for aero engines, especially in the rear part of the low pressure turbine. The main advantage is lightweight. It's a lighter alloy respect to nickel superalloys, and so this promotes an overall weight reduction. And you have an higher strength on density corrected basis, so you can also produce taller blades without increasing the overall weight of the engine. There are new potential applications, but there is still debate about that. Again, in aero engine for high pressure compressor blade, but there is a limitation on that. And in the automotive industry for turbochargers and engine valves, mainly for motorsport nowadays, no longer for conventional cars. So the chemical composition usually it's a more or less a balance between in atomic percentage between titanium and aluminum, and then you have additional elements to promote different properties like corrosion or oxidation properties. This is the reason to introduce niobium and chromium, for instance. The main drawback of these materials is that they are quite brittle. So the strain failure at room temperature is in the range of 1 to 3%. And the K1C, so the fracture toughness, is relatively low. So you have a relatively higher delta K threshold, but the difference between the delta K threshold and the K1C is very narrow, is small. So this reduced the design space very much. So the main objective of this work is to highlight a few. This is basically a side activity, is a secondary activity we have performed on a high niobium alloy. So you have 8% of niobium, 2 chromium, around 45% of aluminum, and the rest is titanium. We have conducted this test with a non-standard subsize specimen, a room temperature with a loading ratio of about 0.0. And the main goal is to assess or to try to understand how the closure plays a role in fatigue crack growth threshold. Materials is produced by EBM, so it's selective laser. It's not selective laser melting, is EBM, and you need to produce the material in high vacuum in order to avoid oxidation and oxygen pickup by the material during production. The final microstructure is this one that I am showing. Is basically the final microstructure is obtained after EBM plus hipping plus heat treatment. So if you ask me about pores, there are no pores technically. Okay, so the material, this type of microstructure is not the target one. It's a mistake, I would say, in terms of microstructure. You would rather prefer to have a smaller colony size of your lamella grains. So out of specimen left over from previous activity, we produce this small specimen that we pre-crack. So we generate a crack by wire EDM. And then we produce a crack ahead of this notch by compression pre-cracking. So you cannot generate a stable crack in titanium aluminides without compression pre-cracking. You go back to the work of Subra Suresh in the late 80s, beginning of the 90s. And there has been major work by the group of Rainer Pippan in Austria, in Leoben, demonstrated that using compression pre-cracking, you can generate a stable crack growth propagation in titanium aluminides. So These are the cracks that are generated by compression pre-cracking. And so there are tiny cracks ahead of this notch. And then after pre-cracking, the whole specimen that has a size at the total height of about 28 millimeters, we sliced in three small specimen. We produce a hole which is slightly beveled, and we started with a conventional fatigue crack growth test. So this again is the microstructure height of the crack tip. So we produced the test by constant force range. So they're applying continuously increasing in blocks, and applying increasing the stress intensity factor delta K until we got a stable crack propagation. So cracks are propagating in this way. So they are quite prone to go around the microstructure. So you have lamella grains, and so the cracks is propagating through the lamella grains, and it's let's say slowed down by the lamella grains, or it's propagating quite fast through the lamella planes. And these are observation also of other cracks that we had in other specimens. So you can see that even if the loading is vertical, you get very these slanted cracks that are propagating within the microstructure in a decohesive or trying to break up the lamella planes. And I will go very fast through these images. It's a repeated concept. So we performed the test in this way. We started with a block of loading, and then we unmounted the specimen, took pictures, remount the specimen, go on with the loading, or unmount the specimen, increase the loading a little bit, and then go on like that. It's a fastidious work by my master students that helped me to do this type of activity. And so you can see that in spite of some principal crack, you have some other cracks that are already generated within this lamella colony in this position. So you don't see it, but you have a long crack going around, and the tip is about here. And again, this is the evidence after a few cycling that the crack has propagated in this way. You just have to consider that this distance is in the order of a few hundred microns. And again, there is a definite evidence of a big influence of the microstructure to the crack propagation. Okay, so this is the more or less the complete picture of this crack that has propagated through the microstructure. And you can observe that you already have some translamellar propagation. And when the cracks is going through the lamella grains in this way, is slowed down. Okay, so you might have a threshold due to the fact that the crack is have a translamellar fracture. So you do have the two mechanisms, the translamellar fracture and the interlamellar decohesion. So the translamellar fracture is you can observe it on the fracture surface by this kind of let's say images. Okay, and this is what is happening in interlamellar decohesion. So in this case, I would say that the material and the microstructure is the defect itself. Okay, so this is again the long history of this propagating crack through the microstructure. Okay, so now we conducted in a few years ago some conventional tests on CT specimen with the same alloy. And these are the gray dots on the Paris diagram that you can see here. And these are the new results conducted with this unconventional sub-size specimen. And you can see that there are a few, you can observe propagation below the long crack growth threshold. So the long crack delta K threshold is about here, is between, let's say, 8.5 and 9 megapascal square root meter. And you do have some propagation also here with the short cracks. So you have a marked effect of the microstructure on the fatigue crack propagation in this case. And you can observe that you have more, the new data shows an increased propagation, and then you have a reduction, and then you have an increase of the crack propagation rate, and again a decrease, and then until you reach a definite long crack threshold. And if you want to propagate the crack definitely, you have to increase the delta K up to 10, 12 megapascal square root meter. Okay. So the rationale is depicted here. Is the mechanism is well known. You have a long crack growth threshold here, and so you have short crack propagation that is, and you have a crack that is slowing down, and then it is accelerating when you increase the delta K, so the available energy for propagation. And mainly this threshold is generated by a crack that is propagating through the lamella planes. So when the lamella planes are perpendicularly to the crack propagation. Okay, so we needed to highlight how much crack growth closure we had the crack we had for this growing crack. And so we did the test according to the ASTM, even though we had this unconventional specimen, sub-size specimen. And we used the offset compliance method to measure the crack the crack closure level. And this is quite standard, so I will not go into details unless you ask questions. And we could measure a level of opening, which is about 35% respect to the Kmax. So you have a definite crack closure effect, which is remarkable. So we try to apply some modeling of this crack closure phenomenon by using the Suresh-Ricci model, which is a geometric model. It's very old, so I will not detail that. It's basically you have to take pictures of your propagating crack and try to correlate this value in the statistical way to the parameter of the model. And by using this model, you can assess that your closure, according to the pictures, would lie into this blue area, but the actual measurement based on the actual offset compliance method gives you a higher closure level. And the reason is that you don't have just roughness-induced closure, but you have other mechanism taking a role, which is crack shielding. You have small cracks forming around the actual crack tip that are somehow masking the loading at the crack tip. And so you have another crack closure effect that is very hard to model in this case. So the new data are also in line with the previous data that we had in initial activity on this side, and this is confirmed that the pure geometrical, the pure roughness-induced closure system is not capable of explaining everything. So my conclusion up to now is that the crack propagation rate that we measured with this miniaturized or sub-sized specimen are consistent with the fatigue crack growth data that we previously collected on CT specimen. The lamella microstructure is responsible for an apparent strengthening mechanism that is bridging crack deflection, crack branching, micro crack shielding all together. So it's very difficult to separate the single effects. The coarse lamella microstructure is less resistant against the nucleation of new cracks, especially when the lamellae are perpendicular to the loading direction. So the cracks are propagating quite fast through the first grains. And the cracks are allowed propagating as short cracks for longer distances when you have a coarser microstructure. And the intensity of this crack closure phenomenon is remarkable because you have about 35% of closure respect to the maximum loading in the region of the threshold. And according to the Suresh-Ricci model, a significant part of the closure phenomenon can be attributed to roughness-induced closure, but is not all. There is more than that, which is also difficult to highlight. So long for now. I hope we have time for a few questions. Thank you very much.